let's talk about dispersion of the dispersion of the light. Okay, so before we talk about that, let's talk about the electromagnetic spectrum. Okay, so this is the electromagnetic spectrum. Okay, so in electromagnetic spectrum, this is the region from this color from red to violet. In simple word, or we can write B I B G Y O R. So these 7 color we can see it. So this is called the visible region. So roughly the red light has the value of this lambda is roughly 700 times 10 power minus 9 meter. Okay, and the other extreme end, the violet, has wavelength of 400 times 10 power minus 9 meter. So the region beyond this extreme end has a different name. So for example, in this region we have infrared. So in that region, what will happen? You know that wavelength will increase. Okay, but the frequency will decrease. So frequency will decrease. Okay, so in that region, those two regions, ultraviolet region and the infrared region, we cannot see it. But we can use this equation every time. Is that the speed of light of electromagnetic wave equals wavelength times frequency. Okay, so frequency will be same. This frequency will be same every time if it moves from one medium to another medium, but this lambda will change when light, say for example a color, say we take the example red light travels from one medium to another medium. Okay, so that's why the speed will also change. The speed will also change in media, changes in different media. Right? So this means if we pass, say for example, if we have this prism, this is a triangular shaped glass. Okay, if we pass light, this is the color is white light. So white light is the combination of 7 different colors. So it is the combination of 7 different color. Okay, combination of 7 different color. Okay, so in short we can write B I B G Y O R. If you pass the white light through the prism, it breaks up into 7 colors. Okay, so for example, at this point, this light will deviate, say for example, this way, another that way. So we can take many up to 7. So this light will deviate at 2 phases, at the first phase, and again it deviate at the second phase. Okay, so we have like this. So this one, first one, is the red one, and the other one is the violet one. So this phenomenon, when white light passes through different media, they have different speed. So these colors, these 7 colors, say V, I, B, G, Y, O, R, has different speed. Different speed in prism, in different medium. So it breaks up into different colors. This phenomenon is called the this phenomenon of breaking up light into 7 different colors is called the dispersion of light. It's called the dispersion of light. Okay, so dispersion light means we can say like a splitting of light, a splitting of white light into its constituent color. Constituent color is called the dispersion of light. Okay, so you see from this picture, light bent at 2 faces. So we can see here, for example, if we take this example, say this is the prism, okay, and if you pass single color, say for example, this color is the yellow color, okay. So this we can call it the incident ray. Okay, so you can say phase like X, Y, G, incident ray for phase XY, right? So when light passes through one medium to another medium, it will bend. Okay, so it will bend like this. This is just a single color. So this we can say, for example, put some name like M, N, say O, right? So NO is the refracted ray. Refracted ray for phase XY. Okay. At the same time, the light will again, when it emerges from air to glass, and again glass to air, it again bends. Okay. So for example, it bends like this. Okay. So OP. So if you consider 4 phase, this is this. So you can say this ray NO, this will be incident ray for phase XG. Okay. So again, you see from here, OP is the refracted ray. The refracted ray for phase XG. So light will bend 2 times. So this is for a particular color. You see, I just take example of this color is the yellow color. Okay. And if we pass not the yellow color, this is the combination of 7 different color, white color, each color will have different speed. So each color will have different speed inside the prism, and it breaks up into 7 different colors, just like that. So this is the dispersion of light. Okay, so I will show you on demo. Let's see here. Say for example, you can see here that this is the light, white light I pass through the prism. It breaks up into 7 different colors. It also depends on the refractive index. So if I increase the refractive index to low to high, the separation of color will change. Similarly, it also depends on the it also depends on the angle of the prism. So in this case, you can see here, you can see that this color, this angle is the angle of the prism. We call it A. This is the angle of prism. This side is called the base of the prism. Okay, so this is the white light. We pass through the prism. It breaks up into 7 different colors. So this is the example of dispersion. Dispersion of light. So dispersion, it also depends on, in the case of prism, it also depends on the angles. So if we change the angle, the separation between the colors will decrease. Okay, it will change. So in this way, we can see that how the dispersion happens in just in a medium, for example, in the case of prism. Okay. These are the examples, like not only the prism, in the case of if we sunlight falls on the droplet of water, we can see the dispersion of light. Okay, these are the examples. We'll see the dispersion of light. Okay, let's talk about the polarization of light. Polarization is light is attribute that wave oscillate has a definite direction of propagation. Okay, so for example, say we have the source of light. The source of light, it will emit light everywhere in all planes, in every planes. Okay, so it will go everywhere. So this kind of light where the plane is not fixed is called the unpolarized light. So this is the example of unpolarized light. Okay, so it could travel in all directions, in all planes. Okay, but we can fix the plane. So for example, we placed a filter. Polarizing filter means where it allows only selected vibrations. Okay, so this, the source that source gives, let's say this source is the unpolarized light. Okay, so if we put a filter here, it only allows the light which axis is parallel to the polarizing filter. So after that, you see that in this case, if we are considering the this light, unpolarized light, it could going to vibrate in all planes. Okay, in all path. Now, if I putting the polarizing filter, it only allow the vibration parallel to the axis. So now this light is the polarized light. Polarized light. Okay, this is the example how polarization act. Okay, and so this example tells you that, for example, if we fix in this kind of if we take the transverse oscillation in one rope, and in first example here are in the vertical plane, that's how the wave traveling through here, the axis is parallel, so it will move through this. But if you move the filter or this path, what will happen that we are not getting the wave to this side. So means this acts as a polarizer, acts as a filter. It only allows to pass the wave which plane is parallel to its axis. Okay, so let's see here, for example, in this case, just we understand that if this is the source of the light, say for example, this is the one case we examine, we are taking that it is oscillating in this plane. So if this light wants to pass through this filter, so all light having the intensity E will not pass through this filter, will not pass. Okay, so this is the component, E cos theta is the component of the wave parallel to the axis. So after passing through the filter, only this component will pass. So only this component will pass. So we can state it as a form of law. It's called the Malus law. Malus's law. What it says is that the intensity of the polarized light must be equals to I max over cosine square, say in this case angle is this angle theta. Okay, so this I is the intensity of light after passing through the filter. So this is the intensity after passing through filter, okay, and this maximum value is in this plane. So for example, this is the intensity before passing through the filter, Okay, so this law can be used to find the intensity. So in this case, this is the same example we told before. So in this example, if we are using two filters, one is called the polarizing filter, okay, then other is called the analyzing filter. So for example, if we put this is the source of unpolarized light, it passes through the first filter, it only allows the wave that is parallel to its axis. So it only allows this kind of wave to pass through this filter. So we are putting here the other substance. This is called the optically active substance, which only allow if this plane of the light is parallel to its axis. So if it is not parallel, we don't see any light coming through these points. So in this time, we can get this light only because the axis is parallel to the propagation. Okay, so the optically active and the activity is the ability of some substance to rotate the plane of polarization of light passing through them. Okay, so the rotation is detected through the polarizing filter or the analyzer. So this is again the similar examples that if in first scenario these two polarizer and analyzer, both filters are parallel. If both filters are parallel, then in that scenario, the light coming through the first filter will pass through the second filter. Okay, so intensity will be the same. Intensity of this one and intensity of that one will be the same. But now we can see here, in this case, the axis of polarizing filter and the analyzing filter are not parallel. So intensity of this will be less. Intensity will be less as compared to the as compared to the intensity of the incident wave. Okay, but if they are, for example, if a filter, polarizing filter and the analyzing filter, the axes are mutually perpendicular, say both are perpendicular, there we don't see any light. So in this case, we can see no light coming through polarizer and the analyzer. Okay, so this concept are very useful when people when the, in and people are the people who works for making the different kind of eyeglass. This kind of concept is used in the polarizer and the analyzer. Okay, and let's say this concept of polarization can be used. How we can get the polarization? So polarization can also be obtained by the phenomenon is called the reflection. So the experiment fact is that we incident the unpolarized light through this surface. Okay, so it could happen as usual. Some part will get reflected back in the same medium. This is the reflection. Some part will go come back to the same medium. This is the reflection. Some part will go to the reflection. Okay, so the clear cut concept is that if we have this unpolarized light, then we are getting the both reflection and refraction. So this is also not polarized. Unpolarized light, we are also getting the unpolarized light. But we can change the angles. Okay, we can change the angle. So the key point is here that we are talking about the Wheeler law. What Wheeler law state that the reflected light is completely polarized at an angle of the Brewster angle known as Brewster angle. So what does it mean? Say, let's draw the same picture here. So I have first medium air. Say I have second medium is the glass. Okay. I incident the light. Say this angle, this is the incident ray. And say this angle of incidence is theta A. Okay, so some part of light will be reflected. This is not a quite new concept. This is reflected. Okay, and some part will be refracted. Okay, so this is refracted, refracted ray, refracted. Okay, and the experiment shows that if the angle between incident ray, angle between refracted ray and reflected ray, this angle is perpendicular. Under this situation only, if this angle is perpendicular, then in that scenario, this light, reflected light, is completely polarized. Completely polarized. This is the Brewster law. Okay, so we can say like this. We can draw this angle of, if the angle between reflected ray and refracted ray is perpendicular, then this angle theta A, this theta A, then in this situation this angle theta A is called the polarizing angle, or the Brewster angle. Brewster's angle. We can do some math over here. Okay, we can do some math over here. So this is theta A. Okay, so just write theta A, because angle of incidence is equal to angle of reflection. So this angle is theta B, angle of refraction. Let's do some math. Okay, so we know n sine theta equals to constant. If you use this concept over here, we can write NA for the first media sine theta A equals we are in the second medium, NB, say sine theta B. Okay, so I'm talking about this medium is first medium, medium A. This is the second medium. So we are write this for that and this for that. Okay, second medium. So let's do. So you know from this picture that the sum of all the angles over here. So you can write sum of the angles. We can say theta A plus 90 degree plus theta B equals 180. Okay, so because I took whole complete angle, so I can write theta B equals 90 degree minus theta A. If I plug those value over there, then I will start from here, then I will get NA sine theta A equals NB, and sine theta B will be replaced by 90 minus theta A. Okay, so I can write NA sine theta A, which equals NB. This will be cosine theta A. So I can rearrange that as tan theta A equals NB over NA. Okay. In our case here, you can just write a note. In our case here, NA equals to 1 because we have air for air, and NB is the refractive index of glass. So I can just write tan theta A equals just refractive index of glass. So this relation is called the Brewster law, when this light, reflected light, is completely polarized. Okay, so these are the pictures taken by using the polarizing filters. Okay, so you can compare the pictures between A and B. If you understand up to this point, you can answer the question of the practice 4. Okay.